Hello there, and welcome to eFits Question Time with me, Joe Hammond. You caught me reading one of my favourite bits in the regulations, Part 3, Earthing Arrangements. Now, I do love reading about those different arrangements and how they affect the electrical system, which actually reminds me of a question I got sent the other day from Nathan. And he asked, "Hi Joe, I'm a second-year apprentice and I was on a job carrying out an EICR. My electrician shouted through, 'What is the earthing system?' Problem was, I couldn't remember. I know we've covered it at college, but I can never remember the different types and why they're different and why that even matters. My electrician tells me it's one of the first things you need to check on any job. Is he right? Yours gratefully, Nathan." Now, Nathan, that is a great question, and your electrician is right. It's really important that we know and understand the different earthing arrangements on an installation. But what are they? Well, the most common types we have are a TNC-s, that's terra neutral combined separate, TNS, terra neutral separate, and TT, terra terra. A good way to visualize these systems is to imagine the journey the cable takes from the substation, that could be the green box at the end of the street, or the grey transformer on a telegraph pole, to the installation itself. So let's start with TNC-s systems. Now, the cable comes from the substation, underground normally, and it has two live conductors, a line and a neutral. The neutral is connected to an earth stake at the substation, which is in turn connected to the centre point of the star transformer. And when the cable reaches the installation, an earthing conductor is connected to the neutral, in that the earth and neutral combine. Now, that's where the C comes from. The earthing conductor then separates. That's the S. What this connection allows is what we call a fault path, whereby if in the installation a fault occurred where the line and neutral or line and earth touched one another, a current would be present in the neutral or earth. Now, this current would then flow down the neutral under the ground all the way back to the transformer where it's connected to the star point, then travel back down the line conductor all the way to the installation where it would go through the protective device, and hopefully there'll be enough current for the device to trip. We call this the earth fault loop path. Now, on a TNS system, the earth fault loop path differs slightly, whereby the line and neutral travel from the substation and the neutral is still connected to the star point of the transformer. However, a separate earth is also provided. Normally, it's the outer sheathing of the cable. Now, this incidentally is how I remembered my earthing arrangements when I was at college, with the TNS and the S standing for sheathing. It doesn't, it stands for separate, but that's just how I remembered it. Now, you tend to find the method of wiring on older installations, but it can be used in more specialist locations such as garage forecourts or factories which may have their very own substation. Now, as the earth is relying on the outer sheathing of the cable, and the outer sheathing of that cable is sometimes made of lead, the resistance that the fault path has to travel is slightly higher. So although it's okay, it does mean that protective devices need to be carefully selected to make sure they trip in time if a fault was to occur. Now, finally, TT systems is where only a line and a neutral conductor is sent into the installation, and we have to provide our own means of earthing. Now, this is normally done with an earth rod. The neutral at the transformer is connected to the general mass of earth. However, if a fault was to occur, then that fault current has to travel through the properties earth rod, through the ground into the earth stake at the transformer, back along the line to hopefully trip the protective device. This, though, could take some time as the conditions of the ground can alter with the seasons, wet days and dry days, so we tend to provide more protection for these systems. A time-delayed RCD would be a good example of this. Now, these are not the most reliable methods, which is why the maximum permitted impedances are higher. But TT systems are becoming less common now. They are still out there, but in more rural locations. Now, by knowing what our earthing arrangement is, we're able to determine what resistances are permitted on our circuit and compare these to BS 7671. Now, TNS systems have lower resistances, therefore higher fault currents, which means our protected devices can trip in time. And TNS and TT have higher resistances, thus lower currents, and that could impact the tripping times. What is really important though is that every installation is checked and compared to Appendix 4 of BS 7671 to ensure that the circuits conform to the maximum permitted impedances, or ZS's. Now this is a huge area of electrical installations and there isn't enough time in this video to squeeze everything in, so be sure to check out our other videos and free CPD on the website. So there we have it. Now be sure to check out our other videos on this fascinating and important subject, and if you are in a bind, why not check out Gary and Richard's video on fitting the Schneider Easy 9 multi-row compact board. Now that is well worth a watch. But that's it from me. If you have a question, then please feel free to drop us a line in the comments below, email, social media, or contact us at efix.co.uk. Now, if you don't mind, I'm going to continue reading into how best to test one's earth rod. Bye-bye for now.